I was looking at the like the contents of the cartridge. So an internal information area is located at 100 to 00112014F in each cartridge. It contains the following value. Nope, and a jump. Well, let's let's have a little look at that. Then 100 and 103. So here. So there's supposed to be a knob and a jump in there. This could be a knob, this could be a jump. Let's take a look. Page 10. So there's a handy index here. Knob 97. Page 97. Knob opcode 00. So this instruction will cause the this is basically an instruction that does nothing, and this is very often used for for timing reasons. So as a programmer, you want the Game Boy to do nothing for a certain amount of time, and you can use knob instructions to force that. It's actually also used in a lot of hacks. So for instance, some of you might be familiar with the buffer overflow hack, and what that does is it will usually make use of a knob instruction to create like a landing pad for a jump operation to jump in, and then it will execute all the knob instructions that are brought into the system by a buffer overflow, and then after the knob instructions the hacker's coder starts. So that's just a little sidestep, and it says also it costs 4 CPU cycles. It's good to know. And what do we have here? It was a jump instruction. Jump. So there are a number of jump instructions, and they can have different meanings. I don't know for sure what they mean, but there are basically different ways of giving an address. So this probably means jump to this address, the address that is specified in the instruction, or it can mean this has an address, HL, and that address holds a value, and that should be used as the address to jump to. So this is just a bunch of different meanings that can have. So let's have a look. Yeah, buffer overflows are the most common kind of hack. They're like a real hack, not talking SQL insertion or something like that. So let's have a look at the jump instruction. This is opcode E9, so it will jump to the address that is given. We can jump CCNN. Jump or conditional jump. This conditional jump is very commonly used in loops. So you can jump if you reach if like a counter reaches 0, so that's a set flag. Where I got this manual, basically I just googled Game Boy CPU manual, and I just stumbled upon this this documentation, so you can check it out here. Maybe I'll put it in the description of the stream. This is a good idea. Can I edit? Yeah, I can edit. So you can check out what documentation I'm using along with me. And we will also have an immediate jump. 2 bytes immediate value, ls byte first. Well, let's have a look at what kind of code we had in our binary file. C3, so that's very interesting. So we have C3, and that is this opcode. So that is an instruction that will tell us what to do, and this will mean it has 2 bytes that will come after this instruction. That is where we need to jump to. So when I look in this again, this is the first, this is the NOP instruction, this is the jump instruction, and this is then the address we'll jump to, 5001. So let's have a look at the memory table again. So it might be a little bit difficult for you to follow because I'm jumping across this manual all the time. So it's quite useful to put up the manual yourself, because it has a lot of like reference sections that I'm using. So one of the reference sections this is the one I'm looking for. So this will tell you the basic memory layout of the address space of this CPU. So if, by the way, anything I'm saying you're not following, then just ask, because then I will explain it. So this CPU uses a 16-bit address space. So we have 2 bytes of 2-byte addresses basically, and the bits of memory are like predefined sections. So for instance, this section will hold video RAM stuff, so it will actually talk to the video chip, I think. This is the internal RAM. The switchable RAM bank is actually the RAM bank that's inside the cartridge, and we just saw that our cartridge actually has it has like a I think it was 16 kilobit RAM, so 8 kilobyte RAM bank. Only has 1, I think. Oh yeah, this is also very funny. It has you have here internal RAM, and then you have like a copy of the internal RAM, which is going to be really annoying for me to code if programs actually use this section. So I don't know actually if there are a lot of ROMs that actually use this space, but they probably do, because they can maybe use it for like easier jumps and stuff. Use like incremental jumps, so I don't know. So we're looking for 5 something, and that's in our ROM bank. So we have a switchable ROM bank, 32 kilobyte ROM, okay. So 5 something will land us somewhere in the ROM bank. I'm not going to, dive too much into that right now. Okay, this is where we were. We were looking at the cartridge layout. These are the memory locations reserved. So these hold like interrupt addresses. These are like reset addresses. So a certain kind of reset, it will start at that address. Status interrupt, timer overflow, serial transfer completion interrupt. So basically, if an interrupt is called on the serial line, the instruction pointer will point to this address, and you can execute that stuff. So this is what we just looked at, the 100 location on the cartridge. That was really cool to see that we could figure out by hand the first bit of the program. So this is a piece of code that will resemble the Nintendo graphic, and we can't actually probably tell it from these bytes because it's probably like encoded sprites, or it uses like a character set inside the video chip. Maybe we'll come to that later, but it might be fun to check if these bytes are actually inside our ROM. So let's have a look at that. 104 in the ROM. .104 in the ROM. 104. Is that right? I forget. I have very bad short-term memory. Yeah. 0104. 0100 2 3 4. So it starts with CEED and then 666. And you can see it's the same thing over here. So that indeed is the scrolling Nintendo graphic. And if you can recall, I don't know if you have any of you guys have an old Game Boy. If you actually boot it up without a cartridge in it, or the cartridge is not inserted properly, instead of scrolling the Nintendo graphic across the screen, it will actually show like a black box with a TM mark. And I don't also think it doesn't have the audio pling when it hits the middle. Yeah, so this is nice to see that we're like figuring out how this works. Title of the game in uppercase ASCII. Okay, that's interesting. If it is less than 16 characters, then the remaining bytes are filled with zeros. That's cool to see. Okay, so that's a 134. So at 134, so this is 0, 1, 2, 3, 4. And we can already see, because this handy tool has already a nice ASCII conversion, and it says Super Mario Land. So Super space Mario Land, one word, and that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then a 0. So I don't know why they didn't insert a space in there, but okay, that's cool. So that checks out. It's nice to see. What else do we have in the cartridge? Oh, sorry for the fast scrolling. Oh, this is also nice. So we can check if it's for the Game Boy Color or regular Game Boy. So if it's 00 or other, then it's not a Game Boy Color. And if it's 80, then it's for Game Boy Color. So, weird. So, it's probably 00. I'm not going to look at this, it's boring. 144 is the high nibble of licensing code. 144, 145. Nah, that's boring. Game Boy, Super Game Boy indicator. Okay. So if it's a 03, then it probably has some fancy Super Game Boy functions. And then we can look at the cartridge type again. So I previously looked at the cartridge type, but I think I counted wrong, so I'm going to do that again to see if we're doing the right thing. So I'm going to look at memory location 147 on the cartridge. So 147, 0, 1, 2, 3, 4, 5, 6, 7. So that is 147, and it's 0, 1. And 0, 1 means it has a ROM and a memory bank controller. then on 148 it will say the ROM size. And the ROM size is also 1. And that means it's 64 kilobytes, so that's nice. So it's not the RAM plus ROM thing I thought previously, and it makes more sense because this would be the first cartridge released, and the first cartridge has to be very mass produced, so it got to be like a cheap cartridge. And also this game didn't have a lot of advanced features, so it probably would fit in a pretty small cartridge, I reckon. So it's not the smallest possible, but it's a pretty small one. And probably more advanced games like Pokemon, then you're looking more at this stuff. So, you know, megabytes of stuff. Probably somewhere here. Because I think it's a pretty good compressed game, but, you know, Pokemon has a lot of text in it also. A lot of like between quotes, spoken text. So that takes a lot of space. Okay, so let's check 149 then. 149 is 0. So no RAM, no extra RAM. Destination code 14A. So 1, 2, 3, 4, 5, 6, 7, 8, 9. A. I think I count wrong. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A. 0, 0. And the next is the license code 01. More interesting stuff. Yeah, so this is something that that is notable. So in order to like check if the cartridge is inserted correctly, first of all you had the thing with the Nintendo scrolling, but that's probably that's more of like a copyright thing. So people are not allowed to copy that bit of code. So then illegal cartridges would be actually illegal if you would copy them. So that's why they copy off the Nintendo thing. And the second thing is what they do to make sure like all the pins are connected properly and it's not going to crash mid-game, is to run some kind of check on the program. And the way they do that is with a complement check. And this is probably explained in detail further down in his manual itself. But what it basically will do is we'll like take a whole bunch of the program and then run some bitwise operation on all of them. So like all the memory and then you'll end up with some kind of and or. You will end up with some kind of bit or byte, and then that is also pre-calculated and put into the ROM. So if the Game Boy then reads the cartridge, runs that check, it compares it against that pre-saved check, and if it's the same, it will run. If it's not the same, it won't run. And that way you can check if the program is loaded, if can be loaded correctly. And that's actually something that's done inside like network hardware all the time to make sure that network transmissions are going well. So here I have the checksum. Yeah, it says here, produced by adding all bytes of a cartridge except for 2 checksum bytes and taking the lower bytes of the result. But it says the Game Boy ignores this value. So the cartridges do have a checksum in them, but they don't use them. It's funny. But they do use the complement check. Interesting. So, as we saw, we have ROM plus memory controller 1, memory bank controller. So, first of all, why do they need memory banks? And why just not have like a nice big memory? And the reason for that is that there's a very small address space. As I've said before, it's only 65 kilobyte memory space. So, you cannot actually get in our case, a 64 kilobyte program cannot fit that in an address space. So what they will do, you can read segments of that, and you can probably specify some kind of command, and then the memory bank controller will switch banks. So you will get access to the other memory bank. And maybe it's nice to look up on the internet how this looks on the inside of a cartridge. So I'm just going to Google for that. Super Mario Land Game Boy cartridge, and then insides. So we have a nice image of such a system, and so probably this one is probably the memory bank controller. Yeah, that's it, memory bank controller, MBC, and this is the actual memory itself, and this chip will probably communicate with this chip, and then will tell to expose the other part of the memory to the pins. You can see most of the pins are connected to the memory bank itself, and then just a couple of pins are connected to the memory bank controller. So I'm very interested to see how that will work. Memory controller 1 has two different maximum memory modes: 16 mbit ROM, 8 byte RAM, or 4 mbit ROM, 32 KB RAM. Okay. So in the old days, then you would write a certain byte to this memory location, I think, and then the memory controller will pick that up and switch a certain bank. So this is 1 byte, X means don't care, S means memory model select, into this area. So not into that byte, because that's probably a read-only. And then it will select the memory model to use. As is 0 selects the 16/8 mode, as 1 selects the 4/32 mode. So you can like choose to have a little bit more RAM instead of having more ROM accessible. And this section talks about how to access a certain ROM area. not completely sure what they mean when they say writing a value which is this is just 1 byte into an area. But how can I write a byte into an area? Just mean anywhere in this region? It doesn't make much sense to me actually, but we'll see. We'll select an appropriate ROM bank at. So this is the cartridge exposed, and then that's the ROM bank, and so we can use these bytes to tell which bank we want to expose. So basically, the programmers who make the games will then like make sure that they switch to the right bank at the right moment and switch back. So I see there's a newcomer here. If you don't understand anything I'm saying, just ask, because I'm also figuring most of this stuff out for myself. So welcome. So if you put here 1 or 0, then it will put ROM bank 1 exposed. A ROM bank is not available from. It can only be read from. Okay. I'm just going to look at this mode right now because I think that's what our cartridge is using. Okay, so this, for instance, when I put 0, 1 there, it will select bank 1. If I put 1, 0, it will select the second bank. If I put 1, 1, it will select the third bank, or bank number 3, because 0, 0 is bank 0. And then that will address those 4 banks. So I'm going to skip over all the other memory controllers because I can't be bothered reading all the stuff about them, and we're focusing on this one right now. So this is also an interesting section. I've already talked about this slightly. And still not sure where this program like is. Yeah. So I talked about this bits before. This program is located inside a ROM inside the Game Boy. Yeah, but is it like copy? I don't know if it copies the ROM to the to memory 0 and then starts, or you know, it's a bit vague. Yeah, so this is the what they were talking about. This is like the complement check. So they will add all of the bytes in the cartridge from 134 to 14D, and a value of 25 is added to this total. And if the least significant byte is not a 0, so a 1, then the Game Boy will stop. So that basically means the check has failed, and that probably means you haven't read the cartridge correctly. If the above checks pass, then the internal ROM is disabled and the cartridge execution begins at location 100 with the following register values. So these are a bunch of registers. This is for the normal Game Boy, Super Game Boy. This is for Game Boy Pocket, and this is for Game Boy Color. More registers, stack pointer. I'm assuming you guys know what a stack is. And this stuff is in memory, I guess. I don't know why it's listed here. Let me just have a quick look at the memory layout again. Reserved memory locations. No. Yes, this part. So what we saw there were a couple of like internal RAM sections that were being set. Usually the top of the memory is used for the stack. So let's do a little bit of coding right now. And because we need to implement basically a CPU, so I'm going to create a bit of code that will be our CPU component. I'm also putting Python 34 at the top of every file, so I don't forget that it's using Python 3.4, not Python 2. So I'm creating a class CPU, and it will hold all kinds of interesting things. So for instance, we have these registers. I'm not sure how I'm going to use those, but I think I'm just going to make them byte arrays or byte arrays, or maybe just ints. So for now I'm just going to make them all 0, and then in the init function I will set these registers to these values. And I also haven't exactly looked yet what all these registers are. So, but I will use the values for the Game Boy, of course, not for the Game Boy Pocket or Color or whatever. This will be a classic Game Boy. This is 0. We have DE. We have HL. And we have a stack pointer. I've created this utilization class to convert hex to integers. So from utils import hex to int. That will be useful later. So now we'll set those things to be hold actual values. Is 1. So I'm also always using a lot of debug statements because I've never built an emulator before, but I know this is really about, it has to be exactly right. And a really useful thing if you use a lot of debug statements is that you can have a reasonable sense of what is happening in what order, because that's when you're building an emulator, the order of stuff that's happening, that is super important. So that's something I'm keeping in mind. Yeah, I'm not sure what to do about this yet. Forgot the stack pointer almost. SP stack pointer. Yeah, so this is very common. Usually stacks start at the top of the memory. In this case that's FFFE, because FFFF is like the interrupt system interrupt vector, something like that. So our actual stack, that will start at this address and will usually go down. And right now we're also going to make a print registers function, because I'm going to debugging this a lot, so I have a nice function that will print the registers. And also need to put that there. So register print. I'm not sure how I'm going to do this. Let me think. Yeah, I'll just have the and then tabulator and then the value. Yeah. Yeah, this is hardcore stuff. Need to format the AF. Yeah, just something I'm trying to make this work. It's mostly just for fun, of course, but I think I can make at least like the CPU interpreter part, so it will just run a program and it will not, per se output something to a screen or take input buttons. But if I can make that work, then I'm already a happy guy. So I need a couple of these. So we have F, BC, DE, HL. Oh, just one more. SP. So I have no idea if this will work, but it makes sense to me. Then we have this list, and I'm not completely sure what this even means. Like, does it mean this is the initial value of the memory? Because I don't know how would they build that in the side Game Boy. I mean, this is RAM, so I'm not too sure about this. If any of you guys, by the way, have like a reference to another manual or something, that would be more than welcome, because this is, I think this is a good manual, but it's a bit it's not very elaborate, so sometimes I'm not really sure what it does. Okay, here they explain it a little bit. A later version Game Boy could contain different values than these at reset. Always set these registers on reset rather than assume they are as above. Please note that Game Boy internal RAM on power up contains random data. All Game Boy emulators tend to set RAM to all 0 on entry. Yeah, and that's also something that I have done. I've set all memory to 0. And the same goes for the card RAM. Oh, this is also something funny. If you guys remember, if you guys had an old Game Boy, if you would power it off, then when you hit the switch, there's still some power left in the system, so it's going to continue processing, but probably it triggers like a reset vector, and you will have like this horizontal line in the middle of the screen, or I think it was slightly off center. And it also said this here, the Game Boy and Game Boy Pocket screen goes white with a single dark horizontal line. The Game Boy Color screen goes black. Yeah, that's funny. So those are those little things that you remember. Low power mode, okay, that's fine. That's also a nice, interesting feature. So almost all processors have like a halt mode, and then it will stop executing statements, but it will still be available for interruptions. And depending on the game, that will save a lot of power. So this is also a nice thing. So these are the things that you have to notice when you're building an emulator. When the halt instruction is skipped because the disable interrupt is on, then it will skip that instruction. So if you build Game Boy programs, you have to account for that. So interrupts are disabled. This code causes the A register to be incremented twice. That's interesting. Let me read that one more time. Oh, that's really interesting. It actually doesn't count the program counter 1 up. So the program counter is also something that I will want to add. Program counter will tell you what instruction is being executed. I'll probably start it at 0. I don't know yet. This will be 1. program counter, very important. So it will not increase the program counter for one cycle. So and by one cycle I mean one instruction cycle. So when the halt function is called but interrupts are disabled, it will then not increment this for one turn, but it probably already has been incremented by that time. So it will fire this instruction, then it will not increment the program counter, so this instruction will be executed another time. And that can get really complicated. So let's have a look at this. Yeah, I'm not going to bother too much with this right now. Yeah, this is also funny. So this will probably prevent the program counter before being incremented at all. So it just will hang on this instruction. It's interesting. So this manual sometimes seems to be aimed a little bit more at program writers than at emulator makers. That's fine, but and blah blah blah, some assembly. So it will continue explaining. I will skip over this right now. I'll probably give this a read sometime later, because this is a little bit more complicated stuff. Then we have sound. We have timer. I also have to read this, maybe very important. Serial I/O, interrupts. Interrupts, we definitely have to do something with interrupts. V-blank has to do with the blanking the screen. And alright, this is like an interesting feature. So v-blank interrupt is like an indication of the system to tell the CPU, okay, right now I'm not going to process any kind of stuff in the video memory, so do what you need to do right now, because after 1.1 milliseconds I will continue processing the video stuff. So if you want to like load new stuff into the video memory, this is the time to do it. Okay, it's also good to know that you know, you're pressing buttons on this system, and when you press a button in real life, like an electrical component button, it will generate, it will change the signal. So in this case, it will change the signal from high to low. So there's basically current flowing through the button. When you press the button, the current will be interrupted, but it won't be like a clean, I go to ground, I go to low signal, and then back up to a high when you release the button. Usually when you press a button, it will be pretty clean transmission, but when you release a button, it tends to, you know, go to high, maybe to back to low again, or something like that. And that's called bouncing. And most systems have like what's called a hardware debouncer, so there will be some circuits with like some capacitors that will prevent this bouncy signal going up and down into the CPU, because every time a high to low transmission goes into the system, our game wants to do something with it because a button has been pressed and some code will be executed. You don't want that to happen too often because that will cost a lot of processing time, but apparently this system doesn't have that. And that's what it's saying here. Okay, with some special registers. So this is like a register that will be used to determine what's plugged in. So at this register will hold the information on what buttons have been pressed. And depending on what buttons have been pressed, there's a certain content of that memory. And what's being explained here is how you, in a program, would control these two lines to actually figure out what button has been pressed. But you usually don't know that immediately, you have to like read it. And this is what this program does. And we'll get these values. Very cool. Some serial stuff. Yeah, this is like the hard stuff. This register is incremented a certain amount of times a second. Will be really annoying to implement. More timers. This is interesting to know. So different interrupts can come into the system at different times. So maybe I press a button, but then right after that, and by right after that I mean nanoseconds after that, the VBlank interrupt occurs. So that's when the graphical chip will say to the CPU, yo, you maybe want to put out some new data into me. And this is actually the priority that's been given. So when that happens, that what I just described, the interrupt routine of my buttons will probably be interrupted again by a higher priority interrupt, but will not happen in the reverse. So if a VBlank interrupt is being carried out at the moment, my buttons will not be registered at that time. And you can enforce that a little bit stronger here. Sound stuff. Okay, so now I also know what that information meant that was a little bit higher up here. Like when we're looking at the registers, all these stuff, because they are not really, in terms of CPU, they're not really registers, but they are special memory locations, and that's where all this stuff is in. So I'm not sure what I'm going to do with that. I also haven't completely figured out how I'm going to do interrupts, because I want to make it, basically I want to do software interrupts, of course, but how I'm actually going to implement it, I'm not sure. I actually also don't know how the actual interrupt system needs to work. So do I always need to finish my current instruction before jumping to the interrupt routine? Something like that. I don't know yet. I have to figure that out. So this is not very interesting. Not going to look at it because it's not really fun. I think what I'm going to do right now, because it's a little bit more fun for you guys, is to implement some instructions. So at some point we're going to need to, actually fire an instruction. And the way we're going to do that is we're going to basically do it the same way a real processor would do it, and that's to load operation, and then to decode it, and then maybe you need to load some more, but we're going to load it, decode it, and then we're going to fire a method on our CPU class, and that will actually execute the instruction. So that will change maybe a register, increase the program counter, do all kinds of stuff, and then that will actually, and that process will then repeat. And the way I envision it is that we'll have in the main Python file, we'll have like a timer, and the timer will make sure that we are firing instructions at 1 megahertz, 1.04 megahertz, because that's the same speed Game Boy runs at. So every couple microseconds it will start a series of instructions, but because this computer might be very fast or very slow, I don't know how fast it's going to be, because probably it's too fast, then we have some time left in between which nothing can happen, because theoretically the Game Boy would still be busy processing all the instructions. Then we'll wait a variable amount of time, and then we'll refire the instructions. So basically we'll start a timer, we'll do our instruction, then we'll stop the timer, compare how much time we have left in our 1 megahertz interval, so 1 over 1 million second interval, and then wait for that amount of time, and then it will loop back. So that is how it's going to work, basically. Maybe I'll type that out in pseudocode. It's a good idea. So that will look something like this. It will be our loop function. First we'll measure time. Then we'll do fetch instruction, decode, call method, then probably handle interrupts. If we need to on real hardware, there's like electrical signals, but we don't have real hardware, so we need to do it somewhere. So I figure after we do our instruction, we can see if our next instruction is going to be a normal next instruction or an interrupt routine. And then we'll measure time again. And then we'll wait certain amount. So, and this basically will be a while one loop. So that's basically how it will work. And I'm not really sure what would need to be happening if I'm not fast enough. So, because Python, it's not the fastest thing ever. And my programming skills also might not make it fast enough. But then I can just, run at a certain speed. So, basically, that doesn't matter. But probably mostly the sound and the video are dependent on kinds of time intervals. And also what we just saw over there in the documentation is what like this special register has a value in it that's dependent on time. So games can use it for timing. We need to make sure that that syncs with our own virtual time. But I'm aiming it to be a 100% time emulator. And we'll see how fast it will run. So that's basically how it will work. Let's save this file. So back to the documentation. It's boring stuff. More boring. CPU registers, yes, that's interesting. So the CPU in the Game Boy is a Zilog Z80, and it's like a combination of Intel 8080 and it's like a custom thing. It's not very common, but it looks like Intel 8080. And I already see that I have a lot more instructions that I need to basically add to this. So I see that I have I don't know why this didn't occur to me. That is B, C, D, E. I think that needs to be just separate. Oh, I know what this is. Yeah. So what these systems often have is the most of the registers will be 8-bit registers, but there will be some ways to access them as if they were 16-bit registers, because we need to jump, for instance, to certain memory locations, and memory locations are 16-bit. And another system I've worked on, which was a 6502 emulator, it's the only previous emulator I've built. But on that system, they will usually cheat by basically using the first page on the memory, which was also always 00 at the start. So they can use a lot more 8-bit operations to jump in that section of memory. But in this system, you have like pure 16-bit stuff. So, and this is the way they're laid out. So you have AF, BC, via BC, DE, HL, and then we have two purely 16-bit registers, and it will be the stack pointer and the program counter, and those all point to memory locations.